Hello everyone. Today we are here to discuss about the charge state and pH partition hypothesis, its effect on permeability and solubility, and ultimately it affects the process absorption of drug across the gastrointestinal biological membrane. As we know, the term bioavailability, that is the rate and extent to which drug is available in the systemic circulation or at the site of action. Basically, it depends upon two phases, that is first one pharmaceutical phase and second one pharmacokinetic phase. Pharmaceutical phase means it deals with the release of drug from the administered drug product. ME means absorption, distribution, metabolism and excretion of a drug molecule. All these processes which are included in the pharmaceutical phase and pharmacokinetic phase, they are depends upon two major parameters that are solubility and permeability across solubility of drug in the aqueous media and permeability of the drug across the biological membrane. And in this, the charged state of a drug molecule means positively charged or negatively charged, or in short, ionization of that drug molecule play a very important role. And this charged state or charges on drug upon the pKa value of the drug and the pH at the site of absorption. Now, the transport of drug molecule across biological membrane. As we know, the biological membrane, it is lipoidally layered, and drug has to pass from the gastrointestinal tract. It has to cross that lipoidal biological membrane to reach into the systemic circulation. Various mechanisms are involved in transport of drug across biological membrane, that is passive diffusion, pore transport, carrier mediated transport, ion pair transport and endocytosis. Out of this, the mechanism of diffusion is a major transport various drug molecules. According to Fick's first law of diffusion, the diffusivity flow of a mass, or called as flux, is proportional to the concentration gradient of the diffusing species across the region of interest. And mathematically it is given as J is equal to minus D dC upon dx, where J is a flux of compound, D is a differential diffusion coefficient, and dc by dx, it is a concentration difference or concentration gradient across the biological membrane. Negative sign of D, that indicates the current is in the direction of decreasing concentration. Based upon that concept, the diffusion of drug across biological membrane can be studied. So a basic model that frame the discussion of measurement of physicochemical parameters and interpretation of their role in the oral absorption process. It's given as transport model. And according to this model, the flux across the membrane barrier is a product function of solubility and permeability in a saturated solution. Diagrammatically, this model we can see on the screen. It consists of two chambers. Generally consider one vessel, two chambers. One is a donor chamber and another one is a receiver or acceptor chamber, and they are separated by semi-permeable membrane having the thickness of H. CD, it is a concentration of drug in the donor chamber, while CR, the concentration of drug in a receptor chamber. CD means it includes both, that is the ionized drug as well as unionized drug, while CR, it is a concentration or includes both the ionized and unionized drug in the receiving chamber or acceptor chamber. CM0 and CMH, these are the concentration of drug in the membrane. CM0, it is concentration to donor chamber, while CMH, it is a concentration of drug in the membrane towards the receptor or the acceptor chamber. Now when we apply the Fick's first law to the diffusion of drug across the biological membrane, it shows that the passive diffusion of solute, that is flux, is a product of diffusivity, that is a diffusion coefficient at the membrane. At steady state, and if we consider the diffusion of unionized form of drug, because only unionized form can cross the biological membrane, so according to Fick's first law, we can write the transport equation as J is equal to dCm upon dx, where J is a flux, dm, it is a diffusivity of solute within the membrane, and dCm upon dx, it is a concentration gradient within the membrane. At steady state, the concentration gradient, that is dCm upon dx, within the membrane is linear. We can rewrite in form of concentration difference, that is in terms of CM0 and CMH. So we can rewrite the equation 1.2 as J is equal to dm in bracket CM0 minus CMH upon H, where the CM0 and CMH, these are the concentrations in mole per centimeter cube unit of uncharged form of solute within the membrane at two water membrane boundaries. Now, since the measurement of concentration of solute within different part of membrane is drug in the membrane, and we can estimate the distribution coefficient between bulk water and the membrane, that we are denoting as a log Kd. So the previous equation 1.3 we can rewrite in a more accessible form as J is equal to dm Kd in bracket Cd minus Ca upon H, where the Kd, as we said, it is a distribution coefficient that allows to use the bulk water concentration of donor and acceptor compartment, that is Ct, concentration of drug in a donor compartment, and Ca, that is a concentration of drug in a acceptor compartment. E and Cr, they represent the concentration, sum of concentration of all form of charges, that is the ionized as well as unionized drug present In a donor compartment, it is denoted as CD, while the concentration of ionized and unionized form in acceptor compartment, it is denoted as a CR. And this concentration we can measure by any suitable standard analytical techniques. But as we know, Tm upon K permeability, so we can rewrite the equation by 1.4 as J is equal to PE into CD minus CA. But at sink condition, Ca, there is a concentration in acceptor compartment, it is essentially 0, because we are considering the receptor compartment as a whole bloodstream, and immediately the drug absorbed, it is distributed throughout the body. So, or it get distributed, or it is transferred away from them. So Ca is essentially 0, so we can rewrite the equation 1.5 as J is equal to PE. This equation, that is equation number 1.6, it indicates that the flux depends upon the product of effective permeability of solute, PE, and the concentration of solute, CD, that is a sum over all charged state form at the water side of donor surface of membrane. Means it shows that flux depends upon effective permeability of solute across membrane, and concentration of solute, or we can say concentration of drug in a water side, means in a donor surface, means in a gastrointestinal tract. This concentration ideally may be equal to dose of drug unless the dose exceeds the solubility limit, in which case it equals to solubility. So we can state that the flux, it depends or is equal to the product of effective permeability of solute and solubility of solute in the aqueous medium. We know the only uncharged drug or drug molecule can permeate across biological membrane. So based upon that concept, we can rewrite the equation as J is equal to P0 into C0, where P0 and C0 are the intrinsic permeability and concentration of the uncharged species respectively. The concentration of uncharged species is always, that's why J is less than the P0 S0. S0 is a intrinsic solubility and P0 is a intrinsic permeability. Intrinsic permeability is equal to Tm Kp upon H. Permeability is equal to Tm Kp upon H, where Kp is equal to Cm upon CdO. O and H here representing the concentration of drug towards the donor compartment and concentration of drug towards the acceptor compartment within the membrane. CDO is aqueous concentration of uncharged solution concentration of species in the acceptor compartment. So based upon this, we can state that this indicates that the degree of ionization or charged state of drug molecule in the solution at the site of absorption is one of the most important factor that determine the rate and extent of drug absorption across biological membrane. Charge state characteristics of compound depends upon the pKa value of compound and pH of the medium under consideration. So how this charge state of compound and what is the effect of pH of the dissolution medium or medium at the site of absorption and effect of the pK value on the absorption process, it is simplified by the concept of pH partition theory. Owing to the lipodal properties of biological membrane, passively diffused drugs must undergo partitioning from the aqueous environment of GI fluid, gastrointestinal tract, and eventually into the bloodstream. This concept of absorption by partitioning process of drug between water and lipid at different pH is known as pH partition theory of drug absorption, and it addresses the relationships between constant and lipophilicity of compound and the pH at absorption site. The concept of pH partition. So pH partition, it is a tendency of the acidic compound to accumulate in basic fluid compartment, while basic compound in acidic compartment. The reason for this phenomena is that acid donate protons in basic environment and becomes negatively charged, while basic compounds become positively charged in acidic environment by accepting the proton. Because of this, the ionization characteristics of drug have a profound effect on the rate and One important thing is the unionized form of drug only can cross biological membrane, and a drug always try to remain in its ionized form. So the compartment which favors the ionization, drug try to remain in that compartment. So suppose if acidic drug is there, it remains unionized in stomach while it becomes ionized in small intestine or intestinal part. So when it is in unionized form, it is always try to become ionized by crossing biological membrane. That's why acidic drugs can stomach region. While same in case of basic drugs remain ionized in acidic pH, that is in stomach, while they become unionized in the intestinal region and they get absorbed. So the ionizability of compound in aqueous solution is a function of dissociation constant, which is always expressed as pK value of the drug, and the pH of medium, that is negative logarithm of H plus ion concentration. At the site of absorption. Now, this pH partition theory of drug absorption is based upon some assumptions. First one, that is absorption of drug takes place by pH. Then preferentially the unionized form as drug is which get absorbed across the biological membrane, and the drug under consideration is having sufficient lipid solubility. Now, according to the classical Henderson-Hasselbalch equation, the ionization of weakly acidic drug can be described as pH minus pK is equal to log alpha upon 1 minus alpha. Alpha is a fraction of unionized species of drug at the site of absorption. After rearranging, we will get equation, that is alpha upon 1 minus alpha is equal to 10 raised to pH minus pK, or alpha upon 1 minus alpha is equal to antilog of pH minus pK. From these equations, you can state that the ratio of ionized and unionized species of drug molecule at the site of absorption is depend upon the pH at the site of absorption is depend upon the pH at the site of absorption and pK value of the drug molecule. For weakly acidic drug, when pH is equal to pK, from equation we can say alpha is, or 50% of drug is ionized. When pH is 1 unit greater than pK value of drug, then alpha is equal to 0.909, or approximately around 90% of drug remains ionized. pH is 2 unit greater than the pK, the alpha is equal to 0.99, or 99% of drug is remain in ionized form. As we know, only unionized form can get absorbed. So when the pH is greater than the pK, drug remains ionized and it creates problem. There is a difficulty in absorption of species. Now when pH is 1 unit below pK value, that is 1 minus alpha is equal to 0.9, or 90% of drug remain unionized, and when pH is 2 unit below pK value, 1 minus alpha is equal to 0.99, and it will get absorbed across gastrointestinal membrane. So we can state that as the pH at the site of absorption increases, the degree of ionization of drug also increases. Hence, weakly acidic drugs are preferentially absorbed at low pH. Now, when we apply this Henderson-Hasselbalch equation for weakly basic drug, we'll get the equation that is pKa minus pH is equal to alpha minus 1 minus alpha. Rearranging the equation, we will get two equation, that is alpha upon 1 minus alpha is equal to 10 raised to minus pK minus pH, or alpha upon 1 minus alpha is equal to antilog of pK minus pH. Clearly state that the ratio of unionized species of ionized and unionized species of drug molecule at the site of absorption, it depends upon pH at the site of absorption and pK value of the drug molecule. Similarly, when we compare that various conditions for weakly basic drug, when pH is equal to pK, drug is remain ionized. When pH is below pK value, alpha is equal to 0.909 and drug remains ionized. When pH is 2 units below pK value, alpha is equal to 0.99, that is 99% of drug is remain ionized and it will not get absorbed by passive diffusion. Then when pH is 1 unit above pK value, that is 1 minus alpha is equal to 0.9, around 90% of drug is remain unionized, and when pH is 2 unit above pK value, 99, that is 99% of drug remains unionized, and unionized form of drug get absorbed across biological membrane by process of passive diffusion. So we can say that as the pH at the site of absorption increases, the degree of ionization, hence weakly basic drugs are preferentially absorbed at higher pH. Okay, I feel key today what we discussed, that is the effect of charge state, effect of pH of charge state, effect of pH at the site, and pKa value in some simplified way. Further details you will get by referring the references mentioned here. Okay. Hello everyone. Today we are here to discuss about the charge state and pH partition hypothesis, its effect